Hello everyone, welcome to this talk. Zone namespaces, bringing zones to NVMe SSDs. I am Aravind Ramesh, Principal Engineer at Western Digital Research. So, um, so today I'm going to cover NVMe ZNS overview, introduction to zoned devices, and what is a zoned namespace, and NVMe ZNS specification, TP4053 overview, brief characteristics of a zone storage semantics, and zone namespace command set. ZNS benefits, challenges, use case, F2FS use case, and current state of software stack, future expected work in the software stack. This is the agenda. And so to give a brief introduction, ZNS devices are a subset of zoned block devices, and zoned block devices generally refer to devices which expose the media in form of zones. Zones are nothing but logical entities within that media, and we have SMR devices, which are zoned devices, but they're hard disks, and they are single magnetic recording devices. And so these devices also come under the zone block devices. And so another type of zone block device is you can call OCSSD devices. So they are open channel devices, SSDs, and there the device exposes the geography of the NAND chips within the device, and the host is free to kind of select and place the data where it wants to read and write to. And then is the NVMe ZNS devices, which adhere to the TP4053, and today we are going to discuss about that. So what is zone namespace command set? So this TP4053 was released in June 2020, and the NVMe zone namespace command set specification allows host software to communicate with SSD using zones, and it defines the zone storage model and its attributes. So if you look at this picture here, if you assume this as a entire SSD, then it shows that from zone 0 to zone x-1, these are the zones available in this SSD, and this is the LBA 0 to LBA z-1. And the LBAs are contiguous in the sense that after zone 0, the next LBA would be the previous LBA plus 1 instead of resetting. So if you look at this picture, we would get a better understanding of a zone storage model. So this whole, if we assume this whole thing as one SSD with a number of zones, then we can, I'll just go through the certain parameters or attributes of a zone. So first of all, we need to understand that all the zones are of type sequentially write required, meaning that all the zones can be written only sequentially. Random write is not allowed. Random reads are allowed though. And each zone has a certain attributes like a zone size. Zone size indicates the number of LBS per zone, and it is same across the device, and it has to be always a power of 2 value. Zone size, and zone capacity. Zone size has to be a power of 2 value, but zone capacity can be anything greater than 0 and less than or equal to zone size. It is the amount of the writable LBS per zone. Zone capacity helps the firmware to manage its NAND so that it does not have to adhere to the power of 2 constraint imposed by the TP or by the host. And due to certain device NAND characteristics, it is needed that it is difficult to exactly keep the NAND as a power of 2 value without being efficient, inefficient. And zone state. Each zone goes through a state machine indicating its current status. So each zone has a state. We'll go through the state zone state in the next slide. But if we look at this image here, so zone 0, if we look at zone 0, it has a starting LB of 0, and the right pointer is right here, and it shows that the zone has been written until this point, and zone capacity is at 60 MB. So this is just for example, and so beyond 60 MB to 64 MB, it is it's a hole basically. You cannot read or write into that that area. Similarly, here also the zone 1 starts at 64 MB, and right after 60 MB, that is 120, 64 plus 60, that is 124 MB. From 124 MB to 128 MB, again it is unreadable or unwritable area. So this is what the zone capacity and zone size. Till zone capacity we can write, we can read, but beyond zone capacity till the zone size, we cannot use that. There is no NAND there. And another point is the right pointer. As and when we write into a zone, the right pointer keeps on incrementing. If we write 1 LBA, when the right pointer initially is at 0, and if we write 1 LBA, and right pointer gets incremented by 1, and so on and so forth. So this is the zone state machine, and each zone has an associated state machine. That state machine has a set of states, and each state defines the operational characteristics of that zone. Typically, zone starts off from empty state, and from empty state, if we issue a open command, it goes to explicitly open its state. And if we directly start writing into an empty zone, it goes into an implicitly open its state, and it goes to full state when obviously we have written entirely to the zone. However, we can issue a command to make it to transition to full state, even if it is physically not totally filled up. And a zone offline is a state that indicates something is wrong with the zone, or that it is basically unable to service IOs. These are the different zone states. And zone namespace command set. So the new TP4053 is derived from the base NVMe specification, and it retains the base NVMe commands and like read, write, flush, erase, and those kind of commands are retained. And in addition to those, new commands have been added. And for example, the zone management send commands. So this is to manage the zones, these commands. Reset zone command basically erases the zone, in the sense that it erases all the data in that zone. And so let's assume a zone of 64 MB, and the right pointer is at 20 MB. And when you reset this zone, the right pointer moves back to 0, and it's ready to be written again from the start of the zone. And the zone state transitions to empty. And open zone command basically transitions a zone to open state. And a closed zone command transitions a zone into a closed state. Finish zone, this transitions a zone state to full. When I say irrespective of write position, what I'm trying to say is that when obviously a zone becomes written entirely full, the firmware itself or the SSD itself moves the zone state into full. However, the user or the application can also move the zone state to full at whatever the right position. Even if it is not full, the user can send a command to make the zone into transition the zone into full state. So zone management receive commands. This is a command to get a report on the zone descriptor of zone. Zone descriptor is again an attribute of a zone, which basically defines some characteristics of the zone, customizable characteristics that a host wants to maintain. Zone append command. So this is another command. This is a basically a write command, and so with the zone append, writes are issued to a zone's SLBA, that is the start LBA, and the drive returns the LBA within the zone where that write happened. So I'll come to this, why this is needed. So yeah, zone append. ZNS specification mandates that zones are to be written sequentially only. So no random writes. So the writes to LBA in a zone will fail if they arrive out of order to the drive. That is what I'm trying to say is we issued a write to LBA 0, then we issued a write to LBA 1, then we issued a write to LBA 2. Then now, for some reason, and it can happen, that LBA, the write request to LBA 2 came to the drive first. The drive processed that one first. And since the NVMe base specification allows device to complete commands in any order, the NVMe base specification says that you can process it in any order that you get it. So device can and is can process the request to write to LBA 2, but it tries to goes to write to LBA 2, but the write pointer is set as 0, and you cannot write anything to a zone. You can write only where the write pointer is present. So now you are violating the ZNS spec. So it's kind of, these both rules are kind of orthogonal to each other. So one solution is that write request be serialized at the host, and only one outstanding write request has to be maintained per zone, eliminating the possibility of out of order writes to the zone. So what we do is, we from the host itself we send only one write request to a zone, one outstanding request. That is, if you send a request to 0, LBA 0, then you wait until that completes, and once that completes, then you send a request to write request to LBA 1. So it's kind of you're serializing that one, and now the device will not get it in out of order because it's only getting in order only one request. So you don't hit this write error. But this serialization in the host reduces the device parallelism. That is, your IO depth is 1, which is not so good, and increases host CPU overhead. And also, opening more zones to achieve higher throughput may not make sense to applications. And also it is orthogonal to more and more attributes of the drive. So as an application may want to write to only a certain number of zones at a time. We cannot force the application to write to extra zone where it doesn't want to write, just because we have, to improve the throughput, because we are maintaining only queue depth of 1. So that is one problem. Another problem is that the NVMe specification has these attributes called MAR, MAR, and MOR, which define the maximum active resources and maximum open resources. So maximum active resources and maximum open resources basically, tell that what is the maximum number of zones that can be opened at any given point of time in the drive, because maintaining open zones has a tax in the drive, and it has a certain amount of resources, and so this kind of limits the maximum number of zones that can be open at any given point of time. So to improve throughput, we cannot have infinite number of zones, or all zones to be opened at any given point of time. So this also kind of hinders the maximum throughput that we can achieve on a ZNS drive. So all this is while trying to do normal writes. However, zone append can overcome these challenges by queuing multiple write requests to a zone, and the device appends writes in whichever order it receives, and it returns the LBA where the data was actually written. And this is a huge shift from how we do it today. So what we are proposing here is, now you send a bunch of write requests to LBA 0, 1, 2, 3, 4, 5, and all those requests are sent to, again, the requests are not sent to LBA 0, 1, 2, 3, 4, 5 now. When we send a write request in zone append, we send it to the start LBA of the zone. So every request will say, this is to the LBA 0. When you want to write to zone 0, you will say that this is to LBA 0, and this many LBAs I want to write, and this is the data buffer. This is the data that I want to write. So you can send as many requests as you want, until that is accommodating the zone size. or zone capacity. And all those requests can reach the drive in any order that they reach the drive. Now, once they reach the drive will take that request and it will just append to the right pointer. Wherever right pointer is there, it takes a request, writes it at the right pointer. So right pointer increments, and then for that right request, the device returns the value at which the right pointer was there. So it basically saying, okay, I got your request, I wrote your data, and here is the location in this zone that I wrote your data. So now the application has to do an extra job of getting this returned value, and that is where it needs to read the data that it just wrote. So so yeah, so that is an extra work for the application. That is the customization needed, but that kind of solves the serialization problem. Okay, so we just saw how what are the characteristics and specialities of or different things about ZNS, and now just to get an idea of conventional SSDs. So in conventional SSD, as with ZNS SSD also, they have NAND chips, and the SSD controller manages these NAND chips and exposes the storage through a storage interface. But in conventional SSD, all the NAND is managed by the flash translation layer, and there is a flash translation layer, and the SSD is managing the NAND. However, in ZNS, the NAND or the data management or data placement is managed by the host. So in a NAND chip, a NAND chip is composed of erase blocks, and these erase blocks you can only write sequentially within these erase blocks, and this erase block must be erased before new writes, and limited number of erases of an erase block, and each erase block has a life. It has so many program erase cycles, and once that reaches its limit, it kind of it goes bad. The erase block goes bad with the SSD, so that kind of the life of the SSD reduces. So so if you look at this, at a macro level, this is more similar to ZNS, the limitations that the ZNS put. So it's like they're taking the NAND characteristics and bringing it to a higher level of abstraction in ZNS. So that's how things work in a SSD, in a conventional SSD. So now we come to benefits of ZNS. It lowers the write amplification. How does it lower the write amplification? So typically, write amplification is something like how much writes were extra done to the device, and so basically, if the application wrote 1 GB to the drive, and within the drive, if it wrote 4 GB, then your write amplification is 4. Write amplification factor is 4. And when I say lowers write amplification, I'm talking about the device write amplification, not the application write amplification. We have a lot of other applications like RocksDB, which has its own write amplification, application level write amplification. That is, if I create a database of in a key value store, in the key value store, if I create a key value store of like 1 GB, how much actually it wrote into the device. So that is the application level write amplification factor. It can be also more sometimes depending upon the workload. Typically 4 to 5 is common in RocksDB. So that is application level write amplification. So device level write amplification happens when the device is kind of full, and there is a lot of fragmentation in the device, and then the device, I'm talking about the conventional SSDs, and the device needs to reclaim some of its space where data has been invalidated. So I'll show a nice graphic in the next slide to understand this fragmentation in conventional SSDs. So this is eliminated in ZNS, because in ZNS the application can do intelligent data placement, and by doing intelligent data placement, it can avoid entirely the device level garbage collection. So by eliminating device level garbage collection, it kind of uh, reduces the, so garbage collection in the device is the root cause of write amplification in the device. So if we reduces or if we eliminate that garbage collection, then the device level write amplification is almost nil, or one. That's the best case scenario. Uh, and so uh, so it reduces the write amplification, and by reducing write amplification, we are increasing the throughput, because the device is not busy doing its own garbage collection, and all of the device bandwidth is available to the host. And also, by reducing the garbage collection at device level, we are reducing the program errors cycle at the device level, hence extending the life of the SSD. um, and also it reduces memory footprint in the SSD. So this is like um, the conventional SSD maintains this flash translation layer, and with the current SSDs going up to terabytes, 8 terabytes, 16 terabytes, the flash translation layer is getting huge, and to accommodate this and also the other requirements of the storage controller, the amount of DRAM required on the device is also high. So that increases the cost of the SSD. So, but with a ZNS drive, we don't need to have a FTL in the drive. So because the host is managing that and managing the mapping. So that kind of reduces the cost. So you don't need to have that much DRAM, and that kind of reduces the cost. And also in conventional SSDs, the over provisioning of the SSD is typically like 7% to 28%. And um, so by this, what we are saying is that we are paying more by 7% to 28% for the NAND that we get, because that much NAND is there, but it is not available to the user. And that NAND is getting used to accommodate this garbage collection and uh, garbage collection. So with ZNS, that is also available to the user. So you get more NAND for the same amount of money that you spend, and that is one more benefit of ZNS. And predictable latency. By predictable latency, what I mean is that when device GC kicks in, a lot of things are happening. Data is getting copied from one place to another, and some erase blocks are getting erased, and some blocks are getting, the writes are happening, the erases are happening, and while these things are happening, the other requests, read requests or other write requests get delayed. So their latency increases, and typically the uh, the erase time or the erase latency and the write latency is huge compared to a read latency on an SSD, and um, it and these kind of GC activities increases this tail latency of the read requests, and that kind of shows a very bad performance at the host level. But with ZNS, we have kind of eliminated the device level garbage collection, and hence these kind of activities are not happening on the drive, and the latency is kind of predictable at the using ZNS. So yeah, this is what I was talking about, the device garbage collection. So these conventional SSDs have FTL, flash translation layer, which maps logical blocks to physical addresses of the media. And files are written to physical addresses as decided by the SSD. Though, so the SSD is making the data placement, resulting in scenarios where files are with different life expectancy are being stored in the same erase unit. Deleting or overwriting the file causes fragmentation on the drive. So if you look at data, or data, sometimes you can classify data into, by temperature. Like it's a hot data is something which is getting updated more frequently, is getting changed more frequently. And cold data is something which, um, which, is there for a long time. It's not changed, unchanged for a long time. So we can, if we intelligently place these kind of data, it is easier to do a garbage collection from the application level. And so if you look at this picture, we have this files A, B, C, D written here, and they are placed haphazardly in the drive. And if I now delete file C, you can see all the pink invalidated areas. So now we cannot uh, um, reclaim these spaces. For example, if you look at erase unit A and erase unit B, we cannot reclaim these spaces without doing a array cycle on them. And to do a array cycle, we need to copy the valid data blocks within those array cycles into a new arrays unit. So we copy the, these purple ones, purple file B and file D and file A chunks into a arrays unit C. And then once that copy is done, then we can do a arrays on arrays unit A and arrays unit B. So the side effects of garbage collection are apparent only when the SSD reaches its capacity. And so when these kind of activities are happening, so like I explained earlier, the latency is shoot up. And so yeah, so I explained this one. I think the cost of GC is the rate amplification factor, and the number of times data is rewritten within a device after host has written the data once. Data written by the host, example is like if data is written by the host is 10 MB and internal writes done by garbage collection to accommodate the 10 MB is 15 MB, then we are looking at a rate amplification factor of 1.5. And increased write amplification factor kind of lowers the write throughput because a lot of activity is happening inside the drive, a lot of writes are happening inside the drive, and the write bandwidth is not available to the host. And higher read latencies, like I explained again, because of these activities, read latencies shoot up. And increase in device cost because we are doing a lot of over provisioning, and that costs that NAND also has to be paid for. And decreased device lifetime. Device lifetime decreases because garbage collection is doing a lot of PE cycles on these RS units, which otherwise in ZNS may not have been done. So that kind of decreases the device lifetime in a conventional SSD, which is not the case in ZNS devices. So when we come to ZNS devices, we collaborate on data placement to reduce the rate amplification factor. So we enable the host and storage device to collaborate on data placement such that data is written sequentially, and also data with similar life expectancy can be placed together in the SSD. So careful data placement can eliminate the device side garbage collection, leading to higher write throughput, lower read latencies, decreased device cost, and increased device lifetime. So if you look at this picture here, on a conventional SSD, the data is all mixed up. The different applications data is mixed up, and and also here in the ZNS SSD, we can look, we can see that similar types of data are placed together. So if a file of, if application 2 wants to delete its data, it's easy to delete one erase cycle. It's easy to invalidate all the data in one erase cycle and then, erase that, this one. There is no copy needed. There is no copy needed from, valid blocks of some file from application 2. That is what a data placement enables. So if you look at this one, this shows the effects of device garbage collection in a much better light. So if we look at the blue line, it is the write throughput of ZNS drive. This is the green one is a write throughput of a conventional SSD with 28% over provisioning, and the orange one is the one with 7% over provisioning. So here, if we look at this, until this point, all the three were performing the right throughput was same, almost same in all the three. However, at this point, the device GC kicks in, and the moment device garbage collection kicks in, the performance drops, and It has with this 28%, it has dropped to this low, almost 50%, and with this one 7% over provisioning, the device is so stressed that there is almost 20% or 30% of IO throughput of what it could deliver otherwise is on this scene. To do this, we have used a pre-production ZNS drive and a production conventional SSD. So this illustrates the benefits of ZNS. So software stack. Already supported. We have the ZNS support in 5.9 plus Linux kernel, and file systems we have support for F2FS, ZoneFS, and SPDK we have a support. User space libraries and applications, FIO, NVMe CLI, blkzone, libzbd, libnvme are all working today. And in RocksDB, MyRocks, MySQL, and Chem emulation are all being worked upon, and we're expecting to upstream these in the coming months probably. So this is the ecosystem. So these are the SMR drives, and this is the zoned namespace and ZNS drive, and we have support for RocksDB, FIO, and NVMe and F2FS, ZoneFS, ButterFS is upcoming. So this is the software ecosystem. And Linux Null block, zoned block device emulation. Here, Linux Null block driver supports ZBD emulation, providing a simple way to get hands-on experience on zoned devices. So you're worrying, okay, how do I look at a zoned device? How do I get more details? How do I go in depth? So this is an emulation. It uses it uses the system RAM, and it creates a device and zoned device with all the zone ZNS specific as per the specification, and we can play around with this device. So the kernel config has to be, we have to enable this kernel configuration, config block dev zone, and then once we load the null block driver, using these commands, we can create a null block device. And once this device is ready, we can play around with this device. But again, this is not NAND. This would be DRAM, using DRAM. If you have a actual SSD, then it's great. You can use this FIO, libzbd, and NVMe commands to see what is happening, how things are there, and to understand even deeper. So this is the FIO to do a random write. So when we say random write FIO, we have added support in FIO, but when we say random write, the zones are selected in random, and the writes happen sequentially within those randomly selected zones. So the name this workload may be a bit confusing, but it still writes it the zone in the zone sequentially. Only the zone selection is random within a ZNS SSD. And ZBD comes with a libzbd, and it gives basically a report of how many zones are there, what is the zone size, what is the capacity of the zone, what is the zone state, and what is the attributes, and those kind of what is the zone index, and those kind of information. So now we want to talk about F2FS ZNS support. So F2FS is a log structured file system which by definition writes all data and modifications to that data to disk in a sequentially log-like structure. F2FS zoned block device support was added for SMR devices, I think in kernel Linux 4.9. It was available from a long time. What I have added is the support to do work with zone capacity. So SMR devices don't have the zone capacity concept. Zone size is what they have, but in ZNS there is this concept of zone capacity. So to accommodate zone capacity, we needed to add some support in F2FS file system. So if we F2FS does in-place updates for its metadata, and in LFS mode, data is written sequentially to the segments in the main area. In a non-LFS mode, F2FS sometimes does in-place updates to data also. So we need to have it in LFS mode. And to host a F2FS on ZNS device, an extra regular block device is needed to host the metadata of F2FS along with the ZNS device. So F2FS does in-place updates to metadata, but it is not in-place update is not possible on a ZNS drive. So the idea is to have a regular block device and ZNS, along with ZNS device, and merge them into create one F2FS volume, and then use that F2FS volume to create the F2FS file system. So if you look at the disk layout, they have F2FS file system has the super block, the checkpoint, segment information table, node address table, and the segment summary area and main area. Main area is where the data goes, and all the other areas are metadata areas. And so when we do a format, basically the main area comes into ZNS device, and all these other areas go into regular block device. So main area consists of sections, and each section consists of segments. So this is how the disk layout is there. Now, so each zone, a ZNS zone, is mapped to an F2FS section. So the section size is equal to the zone size. So this was already there. But the problem is that now zone size is not same as zone capacity. So the segments falling, so in those cases where the zone capacity is less than zone size, the segments falling in that range, that is the segments which fall after zone capacity, they are marked full by the file system at mount time. So what we have done is we look at the zone capacity, and we look at segments. We look at segments which fall from zone capacity and beyond till zone size. If any, and we mark all those segments to be as full, which means that those segments will not get allocated to writes in F2FS file system. So that kind of avoids writing into areas beyond zone capacity. So if you look at this picture here, the red blocks are the blocks where the red blocks are the blocks where the zone capacity ends. Those segments are marked as full, which means it's not available to basically any writes. And also during garbage collection, these segments are ignored. And if zone capacity is an odd size, then the corresponding segment is used until the zone capacity LBA. So if zone capacity is 60 MB, let's say, then in F2FS each segment is 2 MB. So if a zone is 64 MB, then we have 32 segments in that, because 64 by 2. So now 32 segments are there. And if the zone capacity is like 60 MB, then we have actually only 30 segments in that 32 segments where we can do writes. The last 30, I mean 0 to 31. So 30 and 31, segment 30 and segment 31 are not writable. So what we do is that we mark them as full, and they don't get allocated for writes. But what if the zone capacity was 61 MB? If zone capacity was 61 MB, then the segment 30, then the segment 30 or segment 29 will have only 1 MB of writable space. 1 MB of writable space, and so we manage that blocks also. So none of the NAND gets wasted because of this alignment issue. So here are the steps to create a F2FS file system on a ZNS device. So we need to have a block device. If a block device is not available, you can create a normal null block device for metadata. No need of not a zoned block device, normal block device. Or if you have a regular another SSD or any other block device, then that should be okay. And also ensure the ZNS drive is having the deadline scheduler. Like I said earlier, zone append is not supported in F2FS yet, and because of that, writes have to be queued, serialized. Writes have to be serialized, and the serialization is implemented in the deadline scheduler. So we have to have the deadline scheduler to these devices. So set the device to deadline scheduler, and here is this is the format command. O is over provisioning 5%, and M is zone mode, and this is the mount command. So once you mount this, you get the F2FS file system on the mount path, and any data you write now goes into ZNS device. And if space is available on the the first regular block device, and if the main area starts from that block device, the data also may go into that area. So now we come to challenges with using a ZNS. By now we would have gathered that we need to modify the applications. No application can run as is. This is not like a plug and play SSD. You plug out a conventional SSD and plug in a ZNS SSD. That will not work. So any optimization or any good things comes with a price. So the price is that we need to modify the applications. We need to modify the operating systems to work with zone semantics. And the applications now also have to manage their data life expectancy or data placement based on the data life expectancy. So by doing that, they stand to gain in performance and in and also in cost. And another issue is that yeah, a lot of file systems are yet to get the support, and operating systems. So more information you can get, the specification you can get here in the nvmexpress.org. It's TP4053, and you can get more zoned storage information in zonestorage.io and in zonestorage.io /introduction/ZNS, and more information on F2FS in the kernel.org, and that's the GitHub link for our RocksDB implementation, RocksDB support for ZNS drives. Yeah, please do rate this session, and thank you. Have a good day.